So why we need to bother about neural networks in the first place? So far, we'll be discussing tabular methods. Tabular methods represent each state as a separate row on a table. What is the problem? The problem is that there are too many states. Go has 10 to the 170 for big boards. Backgammon has 10 to 20. Real world has a huge, enormous continuous state space. Not only we cannot visit every state, not only this, but even if we visit some of them, we cannot learn anything about others. Extremely similar states, exactly because we represent them are discrete, completely disjoint entities. If you represent your state as row on the table, this means that every state is very different than everyone else, and all states are equally different than dissimilar. And we know this is not the case. States cluster, right? So we want to exploit such clustering, and although we visit some states, we'll be able to generalize our knowledge to states that we haven't seen. So we're going to use function approximation. So this means that instead of saving a state as a row on a table, we're going to fit the representation of the state, as we see here, ST, to a function approximation, which is going to spit out as output either the state value function or the state action value function. Okay? And why this is a good idea? Because such mapping function can exploit similarity between different representations of ST. This state and this state are very similar. This state and this state may be dissimilar, and this is going to be captured by this mapping function. Okay? We can train this mapping function theta to represent such similarity of the states. Okay? For example, imagine you have an agent that wants to navigate in the world, wants to go, for example, to the door. The color of the carpet of the room is irrelevant. Okay? So even if I'm represented here with a completely new carpet, okay, I should still be able to, walk around perfectly well, and such, function approximation should allow me to do that. If every, state of the room would be different row of the table, each time you change the carpet, you say, oh, I don't know anything now. I really need to explore again. Does this make sense? So this mapping functions needs to learn what's important and what's not important, and to ideally ignore what's not important, and in this way bring dissimilar states close by and share information across. Okay? Why else we care about such mapping functions? Because so far in the course we've been talking about states and states and states, and in fact the book will always be talking about states, but the truth is that the harder problem is how do you get to that state representation? How do you go from your raw sensory input, visual, auditory, tactile, to your state representation? And I think this is exactly the exciting part, that you can use mapping functions or neural network architectures to distill knowledge from your sensory input to the state, to your action value functions or policies, action, probability over actions. Is this clear? And this is often known as end-to-end reinforcement learning, okay? Because it doesn't require an engineer to take the sensory input and distill it into some hand-designed ST, state representation. Rather, we learn all the way from sensory input to map to our value functions and policies. And we'll get to this point soon again. Does this make sense? Yes?
So if you just take sensory inputs, is this still an MPP? I mean, still an MPP?
You can learn to squeeze so much information from your input, right? Like sequence of inputs, so that the state inside the neural network is still Markov, right? Mm-hmm. Yes?
Are we using the neural net to learn the mapping from observations to actions directly, or are we learning from observations to state representation?
All right. So you will see in a little bit, in a few slides, we will learn the mapping from observations to, let's say, action values, okay? So the state is encountered in the different layers of the neural network.
So in that case, we were getting back on this question.
Well, pick a layer and say, okay, here is my latent state. Okay.
So the hidden events represent states.
Yes, they capture the state of the world. And they capture that state of the world in the best possible way. For example, they can learn here that these tiny little illuminations of how the light is reflected around is super unimportant for the task that I care about, which is who is paying attention or who is not paying attention. We will see concrete examples, and these are going to become very obvious soon. Now, let me say, first of all, that, of course, as you go from ST to OT, you can imagine being, long videos, right? That the robot sees, the navigation agent takes as input and needs to decide what needs to do next. So this is huge, very high dimensional. While VST, potentially because it's high design, it would have been like, okay, this is the free space, an object at 30,30, another object 20,20, much, much more succinct representation. So to learn all this mapping, you'll require way, way more data, and this poses a very big challenge, but there are ways to get around this challenge, and this is an active area of research, and we'll see solutions this year that we didn't have last year, for example. Yes?
The mapping from observations, isn't that done typically by perception engineer and perception team? Give our own.
All right, so we say we have a company, and there's a perception team. We'll take the observation, make a state, and then will be the RL team will take the state and make the action value function. Is this what you're saying?
Yeah.
I wouldn't say so. You will see in a little bit. I would say we have a deep net, and we have the final goal, which is what? Our agent to navigate, safely around the world. And then you say, oh my God, how am I going to train all this huge net? So many layers, so many parameters. And then you go to your perception team and say, guys, do you have any auxiliary task I can put on my network? Like, do you have some, let's say, object detection label data set? Maybe I can pre-train it on, or I can put some intermediate losses. Do you have some image classification? They will say, sure, no problem. We also have some fancy unsupervised tasks that I can do for you to pre-train your features. And then you'll take their features, and you'll see that you're able to learn much, much faster. Okay? All right. But yes, so we'll see exactly this. We will see this type of, I'm not sure we'll see it today, but we'll see it soon. Yes? Yes?
What are some of the examples where this works?
Say it one more time.
What are some of the examples where this works?
To give you one example where this works. Okay, for example, let's say we want to learn to drive. Okay? Very simple. We have a racing simulation. And, we can play quite a bit there, millions of simulations, right? So we will learn to drive in simulation very well. The problem is that the simulation visuals are very different than the real-world visuals, correct? So once you go to deploy, the policy that you're learning simulation is going to kind of break. So what are you going to do? You go to your perception team and say, guys, let's pre-train the first 20 layers with labeling of where the road is, and where the pavement is, and where the objects are. And then let's take the output in terms of labels and train a policy on top of this, let's say, symbolic input. Why we call it symbolic? Because instead of looking at pixels, you will see at label maps. You'll see the road, you will see the pavement, you will see the objects, okay? And then you'll train a policy on top of this, let's say, semantic label input, you got it? And you train this policy, and now your detectors are going to fire well on the real world because we have a very big data sets. In fact, the self-driving companies capture continuously huge data sets of how to map pixels to where the road is, where the objects are, the cars, etc. And you'll take this labeled input and train your policy on top of that. Make sense? And this you will see that transfers very well. Same for navigation. You train your navigation agent inside the simulation environment, and we have fantastic simulation environments now because people have gone around and scanned many homes, interiors, etc. And the visuals look not super realistic, okay? But you'll train your navigation policy not from pixels, but rather from semantic labels. Where's the table? Where's the chair? Where's the free space? And then, because those detectors transfer, people have put a lot of effort on collecting data sets in the real world where they label chairs and tables and free space, etc. The policy that you train on top of this labeled input will transfer. We can see concrete examples of this too later in the course. But these are all great questions. This means we care a lot about, succeeding in the real world. There are a lot of types of function approximators, and we'll consider in this lecture neural networks for the reasons we'll discuss. What is a neural network? A neural network is an arrangement here of neurons. Every neuron is a small function computation, essentially has a small linear part and a nonlinear part. And these functions are arranged. The reason they're called deep is because we have a lot of function composition. The output of one function enters the other function, and the output of the second function enters the third function. All right, so we have compositions. And so that's number one, which is why it's important. And we know that this similar type of compositionality exists in the virtual cortex, at least according to the neuroscientists. But the other interesting thing is that all of those functions are trained in a differentiable way end-to-end. You have your loss at the top layer of the network, or you can also have losses at intermediate layers, okay? And the errors that you compute backpropagate just using the chain rule. So I must say that the requirement is that all those functions are differentiable. You can put differentiable functions there, and there is, let's say, tools that would allow you, using sampling, to backpropagate through them. But at least so far from what I know, is not that effective, in the sense that you cannot easily escape from a local minima using such sampling type of methods. But we will see. Maybe later in the lectures, I'm going to do again a search what happened the last 6 months, and maybe something breakthrough has happened in that domain. But so far, we'll assume that these are all differentiable functions from the beginning to the end. All right? What do you see here? A cut. This is very important. You see when this neuron fires, okay, gets excited, has high activation, and then you aggregate the input images that cause it to fire, and you see a cut. And they say, okay, my neural network has learned to recognize cuts and has learned to recognize faces, etc. And we know that the human brain also has designated areas to recognize faces and to recognize, let's say, important things that you see every day. Yes?
Isn't there, an open question into learning that we do not really know what it represents? So, is there
Sure, we do not. But there are tons of papers that say, you know what I'm going to say, if this knows, I don't think this is a great way to understand that it's a cut neuron, but they say, what I'm going to see, I'm going to look at the excitation of this neuron, and I'm going to aggregate the inputs, like the images, that cause this neuron to get excited very high. The other people say, I'm going to propagate gradient and see where is the heat map, where this output, is really localized on the input. And some of them work really well. In fact, you can train your network only for classification. Actually, why don't we wait till we get to there? And despite the fact that you train it only for classification, you can take its output and really see, in which part of the image really the network thinks that, this label sits.
So essentially, you're arguing that the mapping of states. So if you said before that nodes in that deep net or that neural net can represent some state. That's what you said earlier, right?
Well, that's what this shows, yes. This is true for particular, let's say, templates. Usually, exactly, the reason that this is not easy to distill in that form is because the power of neural representations comes from the fact that they're distributed. A set of nodes together jointly holds the concept of a cut. Right? And this is where their power comes from. And we'll see this very concretely in 7 slides from now. Okay? That's why it doesn't make a lot of sense to take a neuron and say, okay, where does this neuron get excited? Well, maybe this neuron wants also its company to get excited together. Does this make sense? Yes, but there are other techniques, beautiful techniques, that go from the output layer and, try to localize which part of the input, if I change it, causes the maximum change in the output. And I think potentially these are better ways to kind of see which part of the image really holds a label. We can have a small, this lecture is not about, interpretability and of the neural activations, but we can have, a small type of section in a later lecture about this. Very quickly, because I think most people know, this is one neuron, and these are the input to this neuron. And we have one weight, this is one scalar, right? And this is a bias, again, one scalar. And we have this multiplication that you see. So this is the linear part of the activation, and its output is good. We're going to call it pre-activation. Now, the result of this linear part is again one scalar, and will enter in this nonlinear function. Okay, and there are many different types of nonlinear functions you can choose from: ReLU, tanh, sigmoid, etc. And the output of the nonlinear function, we will call it output activation. And why you need nonlinear functions? Because if you just stack linear functions, if you compose linear functions, at the end of the day, you only have a linear function, so you do need to add nonlinearities in there. Okay? Let's see a beautiful diagram. Here, imagine that you have only two inputs, two numbers, all right? Extremely small input. It's a two-dimensional input. And we have this, then two weights, W1, W2, and one bias. And this is how is the output of the activation of the neuron. And the bias controls where this reef comes from. And the activation here is the sigmoid activation that squishes the output between 0 and 1. Yes, it's always positive, but it's strictly increasing. The reason that in the beginning we thought that propagating here is difficult is because exactly of the squeeze. That's why later people said, oh, ReLU is really a key. But the thing is that other optimization tricks came. So then now even sigmoids are totally okay to optimize. So do you see? So this all the time changes what is easy, what is hard. This is not important. Here is another beautiful nonlinearity. If you go beyond, I mean, it depends on the bias will put you wherever it wants, but if you go beyond some point, there is 0, nothing fires, and then before that you have linear activation. Okay? Now, the important thing to understand is that here is one number, and this unit takes input from all those numbers, okay? And there is one weight to multiply each one of those numbers. And we will use this type of notation. Wijk, the weight from neuron I to neuron J in layer K. All right? Very simple. That's it. So this is a matrix, while this BI is what? For every neuron is a scalar. For the whole layer is one vector. Very simple. Right? Do you guys agree? So now I just stacked. Before we talked about every neuron. Imagine now I have a layer. I have many neurons together. How I'm going to represent their activations? Using this equation. Now alpha x is a vector of the activations of all the neurons of that layer. I would say this is layer 2 because this is B1, W1 here. Make sense? Exactly. So that's it. Not to get confused with what is a scalar and what is a vector and what is a matrix. That's all we need to make sure here. That is it clear what is a scalar and what's a vector and what's a matrix? Okay. That's it. So then we go on, and at the end, here is what we call the pre-activation of the top layer that enters our file output activation function. All right, whatever output. So the important thing, and the one bug that happens all the time, is that the top layer, you push it both through the, kind of nonlinearity and from the output function. Usually you need to, just take the linear output and feed that to your output function. Okay, so here we have multiple layers. Here we have only one hidden layer. Here we have multiple ones, and things go in the normal, the way you understand it. The output of the first feeds the input of the second, and the output of the second feeds the input on the next one. And of course, many of you will know that skip connections are also very useful, and they're used everywhere, which means that you can feed, layer 1 to layer 5 if you want, or to layer 7, etc. Right? And this was a little bit more standard picture, but right now every layer can fit to every other layer. All right? I think the neural network you're going to use will be, a standard architecture. Why we care about depth? Well, here is the output of one neuron, as we saw. All right? So then here, this is it. You have two hidden neurons. Once you combine them again for one more layer, you have this very complex partitioning of the space. So in some part of the x1, x2 space, you have low, and in another part high, and then again low, right? And the more layers you put, the more complex can be this function. So that's why if you can say arbitrarily, it can arbitrarily, approximate any function that you want. So the first layer had this very simple partitioning, and as you go one layer up, you have this super complicated partitioning, right? Very beautiful. Now, if you have enough hidden layers, just how many hidden layers you need, you can partition the space arbitrarily well. Now, the problem is that you need an exponential number of hidden layers for a hidden units in a single layer to do such partitioning. That's why they say in practice, despite that the theory tells you you just need one layer, in practice you need depth, right? Because otherwise you need too many units to do that. And the theory doesn't tell us how many, but it says just enough, okay? So that's number one. The second problem is that the optimization with this single layer, which is just simple gradient descent or gradient descent with momentum or some other simple rule, may never get you to the right solution. So depth is important in practice to get to complex approximations. Yes?
That sounds so much like overfitting.
Overfitting what?
Like overfitting your data between an arbitrary partition space.
Absolutely, yes. And this is super, super, super important. If you put a deep net, you can always fit your data perfectly, except if you have a bug. Like you didn't standardize your input or something is very complicated. With enough capacity, you should always overfit on your training set. So then what you're saying is, how do I know that I generalize?
Should or will overfit?
You will. You will. And if you don't, you just add more capacity and then you will overfit. Does this make sense? Yeah. Right. So what we care here is not to overfit to our training set, although to be honest, they say if you overfit on the visual world, computer vision is done. You just need to overfit to whatever is around. You know what I mean? It's not that complex what's around. So if you have enough data and you overfit, this is good. In any case, we will always have train and test, and we'll always have domain shift between train and test. And we'll discuss right now why you need regularization, why regularization is very, very important, all right? And now you're going to say, why don't we just make the neural network smaller? This is going to appear in next lecture, in next slides, okay? So for now, we say, okay, we have a deep net, and it's huge, and we can overfit very well. And how we're going to train? Well, we'll put our favorite loss function, let's say image classification, and we always need the regularization. And what people use as regularization, the norm of the weights should be small. That's the simplest thing that you can do, okay? And in fact, the regularization is always by default. I don't know if there are fantastic deep learning packages out there. The default is, there is the regularization. You don't need to even think about it. It's there as soon as you instantiate a layer. Does this make sense? Great. So if we want to classify, we want to minimize classification error. If we want to decrease, we will want to minimize regression error, which means Euclidean distance between your predictions and the ground truth. All right? And how we'll take gradients? Well, if you have a very, very big training set, ideally, you want to go through all your training examples, compute their gradients, average, and take a step. This is impossible, right? Because you have a very, very big training set. So what happens in practice is that you do what we say stochastic gradients. You grab one example, compute the gradient, take a step. As you understand, this gradient computed from one example is way more noisy than the gradient computed from many examples. Do you guys agree? Let alone if the examples that you feed in there are generated by an engine, sequentially acting with the world, that are extremely correlated. Like if I start interacting here, all the examples will concern this area and will never concern the area in the back of the room. So now if you take gradients, okay, based on these very correlated examples, you'll probably send the network in a very bad situation, very bad. That's why experienced relay buffers are very important. They say, you know what, gather your samples, but don't feed them directly to learn from them. Just put them in a bucket, let them mingle with all your, recent experience, and then randomly pick from the bucket, take gradients on. Does this make sense? Also, in practice, we don't take gradients based on one example. We take a mini batch. Mini batch is one small set of examples. You compute the gradients and you average, all right? If the GPU memory is your bottleneck and you cannot have a big batch, a big mini batch, what do? You increase momentum. Or what we say, you accumulate gradients, all right? Although people have said that, you know what, if you, let me see, do we show the momentum here? Well, so the momentum essentially adds the gradients from previous steps. So you have memory. You don't just take gradient based on your current mini batch, but also from previous mini batches, all right? The other thing that you can explicitly code up in your deep learning package is that I'll push one mini batch, but don't take a gradient, just compute it, and then I'll push another and another and another, and after I push, let's say, 20 mini batches, then take a gradient. So then, still the training is going to be slow, but at least your gradients are not going to be noisy, all right? Now, the beauty of coding these architectures nowadays is that you have these tiny little blocks that each one computes the output with respect to the input, and you fire them one by one in your computational graph. So now all your architecture or your neural network architecture is a computational graph where the signal flows from top to bottom in the forward pass, and the error flows from bottom to top in the forward pass, and the error flows from top to bottom in the backward pass. All right? And oftentimes the gradients are even, coded up in these little, functions and the building blocks that you're going to be using. And the only thing you need to worry about is that if gradients of blocks that you choose essentially cancel each other or, do not interact well, and, if you combine two blocks together and you simplify potentially the computation, the gradients are going to be much easier to flow. All right? But in practice, the blocks that we're going to be using, they're not going to have such problems. Yes, this is exactly says that we take the gradient, and this is the momentum term that remembers gradients from your previous step of the optimization. T, the time step T, essentially runs during the mini batches and essentially orders the mini batches the number of the times you take gradients. Okay, so this is the most important thing. How do we guarantee that we generalize? How do we regularize beyond asking for small weight norm? Well, an obvious thing is you have a validation set, and you check when you start overfitting, which means your validation error starts going up. Once you see that the validation error starts going up, you stop. So this is called early stopping. Early stopping is a form of regularization. Okay? Why we do not make the neural network small to prevent overfitting? Because it's going to underfit, right? Because the theory tells us that, you really need big nets to make, the situation of you getting stuck in a local minimum exponentially improbable, okay? Once you make the neural network small, you cannot really optimize, so the idea is that make it big, and as LeCun says, regularize the hell out of it. And how can you regularize? You can augment your data, and in fact, this is the most, effective. It's a winning key. How do you augment your data? The simplest thing you can do, you have images, you have labels. Instead of just feeding this particular image so that the network really memorizes where every pixel is, just do some random crops, some random, shears of the image, okay, shear transformations, and then feed it in, all right? So one image now will, generate, let's say, 500 or 1,000 different examples. And this is very, 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 very effective. So that augmentation is the key. Actually, I'm going to show you in few slides an object detector trained only from such data augmentations with only one true positive example. So just 1 second. Now, since we understood, neural networks, let's go and check what happens with recurrent neural networks. Why we care about recurrent neural networks? Because our agents, they don't just open their eyes, act, and then go back to sleep, but rather they open their eyes, they act, then they see a new observation, they act, they see a new observation, they see a new observation, right? So there are sequences of observations, okay, that you want to fit and you want to learn from. So the question is, all these neural networks that we showed before, the input has a fixed size. Do you remember the input? Say, okay, 100 numbers, or an image of, let's say, I mean, we're going to see images soon, but the image should have 50 by 50, for example, size. Okay? How can you fit multiple images? You can say, you know what, I'm going to stack multiple images. I'm going to stack 4 at a time. Well, yes, but what if this time step is 4, next time is 5, and 6, and 7, and 8? How can you take input that have variable length? Does this make sense? So recurrent architectures can take such input. Why? Here is your input at time step t minus 1. Here is your input at time step t. Here is your input at time t plus 1. Okay? At each time step, you go, you compute something, and then you spit out your output, if you want to have output. Probably what action you should take. Now, in the next time step, you're going to have this input, and you're going to have also this state of the previous time step, the hidden state. You fit both in, you predict again. Now, the state has changed. You take the next input with this changed state, feed it, but hit predict again, and so on and so forth. And the interesting thing is that the number of parameters does not grow linear in time. Why? Because the same weight matrix is being used at every time step. Okay? So there is weight sharing in time for those architectures. And the important thing again is not to mix what is a vector, what's a scalar, and what's a matrix. If you have a layer of, let's say, 4 neurons, every neuron takes input from all neurons of the previous layer. Okay? It's not like, oh, this neuron should fit to that neuron. No. All inputs fit to every neuron here. Does this make sense? All right. So here is these equations again. Ht is our hidden state. What is our hidden state? Let's say a vector, a long vector. Okay, it can also be, if you want, a grid. If you have convolutional STMs, it's a grid. It can be 3D, whatever you want it can be. Let's assume it's a vector, all right? It takes, you see W, it's a matrix. So every, component of that state has been computed by taking multiplications with every component of the previous state, all right? And, I mean, okay, we're not showing here the bias, but it's not important. The important thing is to remember that we have multiplication both with the input and the previous state. Extremely simple, okay? The basic RNN equation. Extremely simple. And here is a softmax. We'll see in 1 second the details behind the softmax. So you may see that in practice, instead of this simple RNN equation, other equations are used that are called long short-term memory or GRUs, okay? They're a bit more complicated. The updated equations are complicated. Why? Because they have designated gates. One gate should take care of whether every point of the hidden state should be affected or not. Should I forget it or not? Should I reset it or not? And in practice, it's much easier to control whether you should update or not the hidden state through those gates as opposed to through these, matrix multiplications, okay? So first you decide, should I touch the state? And once you decide you can touch the state, then you go and manipulate. Once the gate allows you, okay? It's very difficult with this very generic matrix multiplication equation, all right? This matrix multiplication, let's say, assignment, to say this particular part of the state, please do not touch it. It's extremely difficult, okay? That's why we put all these gates and we make like this control unit, essentially learn when to touch and what to touch, etc. It's not very complicated. Here is one use. Imagine we have a neural network to do what? SLAM. It wants to estimate the camera pose. And by the way it goes, like since neural networks came out, from 2013, I remember, they broke the image. Let's discuss about this story later. But isn't this beautiful? Now we have a neural network that can predict your camera change. You don't need hand-designed manual SLAM architectures. We can just learn everything end-to-end. And you fit the frame. You fit first in the CNN. Interestingly, the CNN will come later in the lecture. But then it fits in the RNN, fully connected, and then SE3. What is SE3? The transformation, the relative transformation. What is the rotation, and what is the translation of the camera with respect to the previous frame? Does this make sense? And then you put your loss, because hopefully we will have some supervised set to train this relative camera motion prediction, and then you propagate. And you know what? Even if you don't have such a supervised training set, there are ways that you can train unsupervised similar to, let's say, SLAM type of losses. But this is not important for now. The important thing is to say that you have a video, you want to estimate camera pose change in every frame. What are you going to do? You will use a recurrent neural network. Why? Because your input changes every time. And now you may say, why should I use a recurrent neural network? Why don't you just take 2 frames, feed them in a CNN, and predict the camera pose change? And then again, 2 frames, feed them in a CNN, predict the camera pose change. Can somebody answer this question? Why would we model this problem of predicting the camera pose change from one frame to the next with a recurrent neural network that has CNN as a subpart, as opposed to just using, from the CNN, forget about RNN, and go all the way and predict, the transformation and take the loss?
With your smoothness?
Yes, you take into account also which was in your previous frame the camera pose, right? And implicitly, it allows you to smooth in time. Like say there is some more uncertainty in this frame, then you may trust more your previous frame. Okay? Yes?
So we're talking about weight sharing and each time itself. So would it make sense to maybe have different weights for a K time set, and then after K times it have like say 10 weights, like weight sharing
For small.
yeah.
That's a good question. And what I had done when I wanted to capture both, actually it is even in the slides if you allow me to make progress. To capture small temporal context, the easiest thing was to just concatenate those and feed them together in the CNN. So this CNN, by the way, this CNN takes 2 frames. Okay, obviously you need 2 frames. But what I'm trying to say is that you potentially can take these 4 and feed them in a CNN. If it's fixed, you don't need to have an RNN. If it's a fixed input, you just put some CNN. Make sense? Why would you? Yeah. Which is exactly this, right? You may have different weights. Yeah.
When we use an RNN, are we making any assumptions that like the state is not changing very much this time, like for one increase in time step?
No, we are not. We are not making such an assumption. The state can change arbitrarily much, and you can learn that this state changes a lot. Okay? So basically, this temporal smoothness that you're saying, why we put temporal smoothness? Well, maybe we learn that each time I do, the next is because I'm about to yawn. You know what I'm trying to say? This is going to be captured by the LSTM. It doesn't mean that if I'm going to do that, I need to stay like, keep the same motion. No, you just find motion patterns, right? So now I'm holding my arm, and it's not going to be like this later. It's probably going to be like this, because maybe somebody does all the time, So this is going to be captured. Here is another RNN. We're going to take a video as input, and we want to predict, let's say, some caption. Okay, we'll predict some words. Well, I'm not exactly sure if this is what it is, but you take different frames. Again, you feed first from a CNN because it's an image, and then goes to this fancier LSTM version. A very important point. What do we mean when we say distributed representations, and why we need to care about distributed representations? Okay? Because it means that the state of the world is held with all the neural, let's say, units in one layer jointly. It's not that every little unit on its own represents a different state. All together will hold the cat, and all together will hold the grass. And in area layers, maybe all together will hold that little edge, or this other edge from another, let's say, orientation. Now, what is distributed on earlier layers may become a single neuron in further layers up, right? But the important thing is that we jointly the neurons, will hold the state of the world. And let's see this in practice. If you want to do nearest neighbors, you need to have one prototype for every part of the state. So depending on how much you want to partition your state space, you know, the number of parameters scales linearly with the number of regions. While look what's the situation here with the number of units inside a single layer of a neural network in ideal case. So let's just remember it's an ideal case. Here you have one. Imagine that each of those has an activation function. When you think of an activation function, you can always think, is it activated or not? So you can think that this is just yes, no. Is it on or is it off? So depending on whether this neural unit answers yes or no, it partitions the input space into two subspaces, correct? Let's add a second neuron, a second unit. Hop, we partition again. So now, although we have only two, we have four different parts of our state space. And if we add one more, hop, so many, right? This is beautiful. So this means that it's not a linear scale anymore, okay? So now that you've seen this, exponentially the number of parameters. And so this result is very important, right? And now, based on these results, we're going to go and try to explain why educated neural networks are more powerful than HMMs, okay? And we'll do exactly the same reasoning. An HMM, how many states of the world can encode? As many as the states in its graph representation, correct? And how many parameters it needs to have? Well, there's a transition matrix, right? That tells you from this state what's the probability to transition to every other state. So it's quadratic in the number of those states, correct? However, here is the state of the world. It's not one-to-one mapping between neural units and states of the world, right? We said that all this together hold what is one state. And imagine that each one of those takes two values. How many states you can encode here with 4 units? You have 4 units. Each unit can take 2 values, on or off, based on the output of the activation function. How many states of the world you can encode? Right, 2 to the 4, okay? Unbelievable, right? Isn't this beautiful? So it's exponential. The number of states you can encode is exponential to the number of your hidden units. This is the magic, okay, of distributed representations. Now, you may say, sure, that's in practice. I have 100 units. I can have 2 to the 100 states. This is in ideal case. In practice, because your optimization gradient descent, you may not be able to discover all those and partition your space in this nice way, right? These 2, for example, neural units learn to co-adapt. Co-adapt means that if the one goes up, the other one also goes up. Ideally, you don't want this. Does this make sense? And there are tricks like dropout that essentially discourage the units from co-adapting. Makes sense? They ask them to switch. We essentially manually switch on and off 50% of them at every training loop. If you care about details and you don't know them, I can add them in the slides. Makes sense? But this is the important thing that we want to remember. And that's why many times it doesn't make sense to grab one unit and say, okay, what do you represent? Do you agree? Great. Now I'm going to talk about a little bit about computer vision. And so that we make a link between, you know, what type of architectures are right now in computer vision and what type of tricks we can borrow in our architectures for reinforcement learning. Do you have some questions till now? Yes.
What is the intuition behind treating them as binary, and because the outputs are continuous, right? So you can
It is
effectively
continuous.
sample
Absolutely,
infinite
yes.
number of states.
All right. But imagine if binary gives you that many states, let alone continuous what's going to give you. Do you see what I'm trying to say? If this is your problem. And also because the activation function, yes, it does have a linear regime, but also have some saturation regime like no activation and then, you know, imagine the sigmoid. But it's a good point because it's easier to run, you know, to just give you a concrete result of, let's say, the exponential, let's say, growth rate. of the state space, okay, with respect to the parameters. If the output is continuous, sure, you can discretize it even more and show that even more, states can be represented, okay? I just put binary because the sigmoid gives you units. Yes or no? Okay, so once we go to computer vision, the problem is that the input has this particular form. Is it two-dimensional? There's some number of pixels here, some number of pixels here, let alone the 3 color channels, all right? And yes, we can say that, neuroscientists always believed that before 2012, the architectures that they were being used that were shallow would never be the answer, because they knew that, this sequential processing is important and this composition is important from what they had seen in their let's say, experiments. So right now, what happens is you have an input image, and you pass it through as what we call a convolutional neural net. And these are the intermediate layers. The intermediate layers before were vectors. Now the intermediate layers are what? 2D grids, okay? And one of those 2D maps, you call it a feature map. And you have multiple feature maps, let's say 256 per layer, okay? And we'll see how these are generated real quick. Well, the first, no? Yes, here we are. So what did we say earlier? Earlier we said that if you have a neural unit, this neural unit better connect to every input, right? To every scalar in your input. This would mean that you have that many weights going into a single neural unit. 2 billion parameters. This is too much, all right? So the first thing that we're going to say, important thing that came out, from LeCun 1989 is convolution, which means what? Every unit can be connected locally to a small patch of the image using, let's say, this patch could be, let's say, 4 by 4. This means that it only requires 16 weights, all right? And then the same unit can be fired with the same 16 weights to the left and to the left and to the left, to the down, 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 as a sliding window, okay? And this is exactly convolution. You slide that kernel, and now you have activations and the output of that kernel in the whole image without, though, having such a huge number of parameters, okay? Right? Because you use the same 16 by 16 kernel. And how can we think why this is possible? Because if I give you as random image, similar statistics will be seen in the upper left of the image. To similar statistics will be seen to the bottom right of the image. I may take a picture here. Your faces can be anywhere in the image, okay? Now, of course, if you take a picture of a face and the face are registered, and always you have mouths down and eyes up, then it would not make sense, potentially on the top layers. You may want to adapt your, let's say, space adaptive weights. In the early layers, though, that they all look for edges and tiny little patterns, sure, you can still share weights. Does this make sense? Make sense? So convolution tells you that statistics, image statistics in space are the same. There is no reason to learn different weights. I can just learn the same weights and apply. And convolution is very simple. You just don't get confused by the word. It's just multiplication, but shifted everywhere as a sliding window along the image. Oh, here you go. This is 4 by 4. I mean, I'm not sure, but this 4 by 4, and this is different 4 by 4, and this is different 4 by 4. By the way, you're not going to have one 4 by 4. You may have many kernels, all right? As many as you like. Let's say 32, 64, 256. Somehow we pick from power of 2, okay? And parameter sharing, and here is how it's going to look. The same thing is applied everywhere in the image. And you take the results, and if this is one kernel, the results of this kernel are going to be one feature map, a 2D grid. Makes sense? Is that clear? And now if you put another kernel, it's going to run another feature map. And if you put, let me see if we have the numbers here. Yep. So this is how it looks like. You have your kernel, and you spit a corresponding feature map. You put another kernel, another feature map. Make sense? And these kernels are what? These are learned weights. This is what you're going to be learning through training. Okay, not this. This is the output. This is the output. This is what we call activation of a layer. That's what it is, or pre-activation, because it's just convolution. You need to pass it through some nonlinearity. Okay? Yes.
Basic question, why power is 2, not in kernel?
Yes, to be honest, I'm not sure. It has to do with the GPU being happier. Okay, but I can ask about this. Up here, how many feature maps we're going to have? 2. How many kernels we have? 2. 16, that's how many weights we need to learn. All right, huge reduction. Oh, here are 10 by 10. It doesn't matter. So when they say filters, they mean essentially this kernel. Okay, so we have now 100 filters. How many feature maps we're going to have? How many feature maps we're going to have after this layer? 100, exactly. So every filter, every 10 by 10 will do like this. We'll take the results, we'll arrange them in a 2D grid, and we'll say this is one feature map. Okay, then the other feature map, 100, all right? Okay, great. This is very simple to get. Yes, so now why we need pooling? Because after one convolution layer, the pooling layer, what it does, it looks at a small subregion and says, I want to record the maximum value in that subregion. No matter where the maximum activation happened, I will record this one in this, let's say, 2 by 2 window. If this is the highest, then this only is going to survive later. You're trying to do a little bit deformation invariant. If, let's say, the eye is a little bit there or there or there, it doesn't matter, you're going to pool. And here is how also it looks like. So this is pooling bottom right, bottom left, etc. So we know, I think most people know about these details. Yes, so we have invariance translations, and it reduces also the resolution. And that's it. So this is how pooling looks like in this big neighborhood. One of them is going to survive, the one that has the highest activation. So a convolutional neural net looks like this. It alternates between convolutions, pooling, here. Convolution, pooling. Here is the pooling, here is another convolution, another pooling, another convolution, another pooling, right? We have a pooling in every feature map, right? Very nice. And just before we go into the interesting things, let's see the softmax layer, which is used every time we want to do a classification. The output of your top linear part is going to look like this, is what we call the logits, the different scores for the different labels. And then you pass it through what we say the softmax layer that looks like this and makes those logits to be a distribution. And also, it acts as a soft argmax. So the one that dominates essentially is pushed much higher than the rest. Okay, that's what we call it softmax. It is argmax, but it's differentiable. Okay. Now, the important thing that everybody knows is that there was a big breakthrough with CNNs in 2012 because they were able to be trained from this huge image database that had 1 million images with labels, okay, associated with labels. Interestingly, these images were pretty difficult, and they only had the label cut without knowing where the cut was. So it was highly non-trivial that training a neural network for classification, right, it would actually succeed. So what happened in 2012 is that we had AlexNet, right, which was the first neural network on a GPU that actually was, big enough to handle this data set, and the GPU, the training was fast enough to, happen in a realistic time. So two things. And see the huge error reduction, right, from here to here. And then the people have continued, changing the architectures and innovating, etc. So this is the first architecture. It's called AlexNet from Alex Krizhevsky, who is the first author in the paper, and had, let's say, 5 convolution and pooling layers and 2 stacked fully connected layers that had tons and tons and tons of parameters, right? So convolutional layers, as we see, are extremely economical parameter-wise, but fully connected layers are not. So interestingly, if you remove the top fully connected layer, which is that many million parameters, you have a tiny drop in performance. While if you remove, many other layers, you make it shallow, then you have a huge drop in performance. All right? I want to say that, yes, the 2 stacked fully connected layers did not survive beyond that time, so that was I mean, we see that there are way more economical architectures that you don't need to waste that many parameters and you get better performance. So depth of the network is the key here. And here is a much deeper network from Google that had a lot of, convolutions, pooling, softmax, etc. And I think it put also intermediate supervisions. Not only supervision at the very last layer, but also intermediate. Why you need intermediate supervision? Because people thought, it's hard to optimize. It's hard to optimize very deep networks because the gradients vanish as they get multiplied and multiplied and multiplied with small numbers. They vanish as you go back. And indeed, now the interesting thing to remember is at the bottom there are convolutions and there is no fully connected layer. There's just one average pool. Okay, average pooling, not max pooling. You just average all the activations on the very top layer. Okay, for average pool to work, every location on that top layer needs to have a receptive field that sees the full image. Okay, otherwise average pool doesn't make sense. And later architectures have used this average pool to see which weights for a particular class activation, how they're distributed in the image. We'll see these attention methods later in the course. But this is an interesting image. Before ResNet, okay, another architectural innovation that was very important and facilitated much the kind of the backpropagation of the gradients, very deep networks were very difficult to train. Both the train and test error was higher than shallower networks, which were 20 layers deep. Okay, so you could not train really, really, really deep networks. So the innovation here of residual networks is how can you train really, really, really deep networks and see your performance improving as opposed to, such being suboptimal. Well, what they said is, I will always allow the gradient to flow in a way that is not affected by choosing this, as we see, the shortcut, okay, which is an identity, as opposed to these multiplications. So then you have this very, very, very deep network, but the gradient, if it follows that path, there is always one way to shortcut and go all the way back. And in fact, there has been architectures that have tons and tons of different paths that the gradients can follow. Shortcut, pass through 30 sub-blocks, pass through 50, 100, 150 sub-blocks. And they offer robustness and they make a lot of sense. Great, so these are basic things that we need to know. Let's go back to our problem, which is what? How can we go from state as input to observation as input? Okay, this is our question. And what type of architectures we should use to effectively take observations as input and compute value functions? Okay? And how can we handle, going from here to here, these two slides are extremely different. S is short, O is huge, okay? So how can I train this end-to-end with, do you see what I'm trying to say? What intermediate loss I need to put, what auxiliary task I need to devise, what pre-training mechanisms to be able this end-to-end method to work. Well, let's start with the first example. It was playing Atari games in 2013. That was the first learning model to successfully learn control policies directly from high-dimensional sensory input. Okay. Before that, there are neural networks that use coded state, right? First of all, we know Didi Gammon, a long time ago, in fact. Okay. The state was short, even before GPUs, right? No problem, you could train. Now, of course, once you go to high-dimensional, no surprise that this came after 2012. Okay. We do need GPUs and all this machinery. Okay, so the important thing is that the image comes as input. Here is the image, here is the action, here is the neural network, and here is your action value function. All right? Did any particular innovation in the architecture happen? Well, the only thing I would like to tell you is here, if let's say you have 4 actions, up, down, left, right, to estimate the action value function of those 4 actions, what do you need to do? You need to feed each one in the network and take the result. So this wastes time. Why should I do that? Why don't I just feed the input, okay, and hope at the output have the value functions for all the actions at the same time? All right, this is way more economical. I don't need to feed every action one at a time. So that's the first thing they did.
Question.
Yes?
Can you please go back and repeat the previous slide?
To repeat the previous slide. So I have no clue what I said. From which part I should repeat?
Why this did not work, and first of all, what is this?
What is this? So this is the following. Here is a neural network. This guy is an image from an Atari game. This is a joystick, actions to play Atari game. This is what? A scalar. What for this action, and that's the image, what is the value of this particular action? You feed all your actions, let's say 4, you get 4 values, you pick the one that's highest to act. Okay? So now we know what it is. What else shall I say?
But again, what is it training on? What is the input data?
Oh, I see. So let me tell you, this is next lecture, so we're not going to talk about this, but the only thing I want you to remember is that this is an action value function. So exactly the same thing that you used, okay, for example, the Q-learning rule, you remember it? You had the target and you can apply it exactly this on this output of the network. But to be honest with you, this is exactly the topic of the next lecture. How we can train our architectures where instead of having tables and to replace their values, we have neural networks. So this is going to be a full lecture. What I want to discuss is, imagine that there is a particular loss here. There is a particular loss. The reinforcement learning will give you those losses. What should be the architectural, let's say, interesting architectural choices that you may need to do beyond convolutional networks for you to do well? Is it important, or we can just put vanilla CNNs and that's it? That's all I want that we discuss. Okay? But imagine that somebody told you what is the ground truth Q and you don't know that, right? You initialize it, and then you play, and then you see if you succeed or not, and then you back up. The same thing as previous lecture.
So this input, this visual input, right?
The visual input.
Essentially, it's not a continuous space, because if I remember correctly from this game,
yes, it's not.
The enemies and like the whatever, shooter, whatever, they have discrete positions, right? So
Okay. Yes, and the blue color of Atari game is, let's say, 120, 113. Yeah.
Okay, so
The RGB values, right?
okay, I just
That's okay.
like again, this could be, if we had amount of time to kill, this could be represented by like a tabular state space, right?
Like the full image to be one.
Yeah, to be one state, because
Yes, so
the
that's a lot
positions
of them.
there are discrete. Yeah, I'm saying.
No, but yes, well, it's very difficult to go and record all the different images. So I think what your colleague says is the following. Yes, this might be a 100 by 100 image, and this may be, that 100 multiplied by 100 states. But in effect, I'm never going to see that many images, right? Why don't they just play tons of Ataris, cluster all possible images I can see and put each one of them as a separate row in my table? Still, there are going to be quite many rows on the table. Does this make sense?
Yeah.
A lot of
it
rows.
makes sense. It's going to be a very huge space, but unlike like a camera feed where the space of inputs and features is continuous, right? There, it's kind of.
So actually, your question is very good, and you will see, guys, that how things are simplified if you play video games versus when you're in the real world. I'll show you papers that make a big, mess about how we can learn features to do good in Atari games, etc. And then they say even random features would work. Just put a network, initialize randomly, and that's it. You don't need anything else. So we'll see this when we talk about exploration via curiosity. Yes.
My question is, are camera feeds considered continuous or discrete? Because they have a fixed number of pixels in each color channel.
Right. So let's not talk about continuous discrete. Of course, everything is discrete, 256 numbers, that's it. I mean, what continuous? The image has been quantized, right? Yeah. It's a very big space. Right. Okay, guys, so we already talked about this. Here is the image, and I'm going to spit all the action values together. How I'm going to train them? With deep Q learning rule, and we're going to see the details in the next lecture. Very simple. The other thing to remember is I'm not feeding just the current frame. I'm stacking 4 frames because I just need a little bit of history. First of all, I need to capture velocity. Where is the ball going? All right, so I need at least 2 frames. Now, if you add a little bit more, it's good. The images start from 2 to 160. You downsample, you crop 84 by 84. I want to remind you that in CMU in 1989, we did have this Alvin, right? That had the 30 by 30 images to feed and to drive a car. So we did have some, let's say, neural network with real images that would, move a real agent, which was the car. But they say that they are the first deep learning model that succeeded with reinforcement learning, which is true, because the car was not reinforcement learning. We had to drive it first, then to mimic us, if you remember the details of Calvin. We will come back to Calvin. Okay, and everybody says, probably you heard in the community, they say, oh, but now we don't engineer the features, but we need to engineer the architecture. And how do we pick the right architecture, right? So what do they mean when they say, how do we pick the right architecture? Right? And then Jeff Hinton says, oh, now the next game is going to be, who is going to design the right network architecture? Do they mean how many convolutional layers shall I put? How big should be the strides? What will be the learning rates? Is this what they mean? Probably this is what many people mean. But I would argue that there are way more important questions to be answered about network architectures. Okay? We may need to devise for example, convolution is one structural bias. We didn't learn convolution. Somebody thought about it and said, you know what? I think convolution can work for this, for this scenario of images because statistics are stationary. So what are the other structural biases that we can think that we can put our neural network architectures to make learning much, much faster? Okay, this is what I want to discuss. And first thing that we need to think is this what-where decomposition. So far, this ImageNet classification that we talked about, that you just take the image and I need to say cat and dog and chair, and then I win if I do correct, guess correctly the label, is all about what? What is in the image? I don't need to know where to do well, okay? But in order to act in the world, and let's say to push this bread in the right place, I also need to know where things are. I need to know precise spatial locations, okay? So how can I add this what-where into my architecture? How can I learn to attend to important parts of the space and forget about other parts of the space? Does this make sense to be able to do way more fine-grained reasoning? Okay. So I argue that we can take inspiration from object detection. Because look at these images. Let's assume we want to get those results. We want to take these crowded pictures and detect every little object. Is this clear to you? I have told you yes. For image classification, you know what to do. Take the image, crop, feed into convolution pooling, convolution pooling, convolution pooling, convolution ReLU pooling, convolution ReLU pooling, sorry, softmax, and that's it. You win. Is this clear to you? What architecture would you use to do object detection? Right? It's a very different task because now you need to localize the objects. And I want to tell you something. Since 2012, the story has always been the same. Yes, CNNs are great in image classification, but will they be able to do object detection? And then somebody does amazing object detection. And then, yes, CNNs are great in object detection, but will they be able to do optical flow? And then, yes, somebody does amazing optical flow. And then, yes, CNNs are good for optical flow, but will they be able to do SLAM? No, there's no way they can do SLAM. And then somebody does amazing SLAM. And then, CNNs will be, let me tell you, I think it's always yes. The answer is always yes. You just need to find the right architecture to get there, okay? And I want to say that to do object detection, optical flow, I assume people know what is optical flow, right? You take two pairs of images and predict the motion of the pixels, correct? We had to do, not we, but they had to be done very important architectural changes, particular for the task. Makes sense? Great. So when we say what architectures to use, you should not think, oh, how many convolutional layers I should put, and maybe we need to put also even an RL algorithm to tell me how many convolutions to put. There are way more important architectural choices that you may need to do, and the CNNs are not given by God, they're given by LeCun, which is a little bit tiny bit different. You know what I mean? But anyhow, so this is the question here. So let's see the first answer, or let's see the first answer. What comes to mind? Somebody that knows already. Would they tell us would you like to tell us what you would do to detect objects? Come on, guys, this is a very important task. Yes?
I would consider detecting edges, like
Edges.
like
Like the closure of the objects.
yeah.
And, okay.
So that's how I would think about segmenting the image. Like if I detected like outlines,
Yes.
then I would. How is that any different from like the original problem where you detect that outline and you crop the image and you keep these outlines in some sort of classification further on?
Right, so I think the answer is not bad. I think your colleague is saying the following. I will rely on outlines of objects and rough edge features, etc., to predict some segmentation of the image into subregions, let's say boxes, and then I can take this box and decide, is this an object and what object is it? Okay, and in fact, it's a little bit further away, but this is how it was done. You take some region proposal algorithm, which is not deep, and what do these region proposals do? They do sliding window, they take features, and in a very shallow way say, is this likely that there's an object in there or not? And they look at things like this, the edge arrangement and the edge distribution, very simple feature, manually engineered features. And they, of course, they don't do well, but we use them as high recall, low precision. You know, given an image, you get 2,000 of these region proposals, all right? Does this make sense so far? So now you take these 2,000 region proposals from a classical computer vision algorithm, and then you take every region, and interestingly enough, you crop it from the image, you make it a little bit larger to include some context, you make it a little bit larger, and then, you know, you warp it, you feed it in the CNN, and you predict, is this an airplane, the person, okay, and now you treat it as a standard CNN, which, you know, it classifies it, essentially you just classify regions, all right? Does this make sense? Now the problem with this is that it is extremely expensive, because each time you take a crop and pass through a whole convnet and classify, interesting enough, I mean, back then, because we didn't even know if everything can be done end to end, you would just take the features and go outside of the CNN to an SVM and classify in an SVM. But in any case, now there is no SVM, everything is inside the network architecture. I want to tell you that there are two losses there. One is classify this box whether it's good or not, and the other is a small regression. You try to deform a tiny bit the box. Now I want to tell you, maybe we should go a little bit more quickly, that this was very slow. 2,000 times you need to go through the network. This is crazy slow. Now the next successor takes a huge image, a whole image, and passes the content through a whole image, not through the region. Does this make sense? This is a huge difference. Here we would fit a CNN in a region. Here we put a CNN in the whole image. So now the whole image, what you get is a grid of deep features. And you have a region proposal network. It's called RPN, region proposal network. You have a lot of anchor boxes sitting around, 2,000 of them proposed. And there is a classification there that tells you pick the 300 most probable ones. Again, high recall, low precision. And instead of taking those and pass them to a deep CNN, you just pull the features within them. Pulling meaning from all this big feature grid on the whole image, if I'm a bounding box, which features fall inside my bounding box? So I just select essentially the features of that bounding box, okay? And then pass through these couple of layers. These couple of layer weights are shared, of course, across all these different boxes that you evaluate. And again, you classify and you regress. Classify, is this a good box or not? If it's a good box, what category is it? And also, how can I deform slightly the box to go closer to the ground truth? Makes sense? So these are very, very important architectural biases that would allow to generate these beautiful results. Now, here's the question. The manipulation community and robotics community doesn't use those detectors right now. And why this is the case? Because we don't have labels for the objects that I care to manipulate. I don't have labels. Let's say I want to manipulate this particular microphone. I don't have a lot of big training set of, microphones to train it on. So all this beautiful machinery that could be very useful for manipulation is being unused because it depends on if you have the right label data. So I want to discuss with you one method that, in fact, you can get around without having somebody label you a lot of training data. And here's what I want to discuss. This is the baseline. You take the input, you pass it through a vanilla CNN, you get some numbers as your output state. All right? And here is another image, and somebody argues that, you know what, it's very useful to detect where the objects are. To detect the objects are. So I'm going to run an object detector, detect those objects, and then for each one of those objects, compute those appearance features, and then append them, and also consider the distance between the detected objects. Okay? And what are you going to do? So now you have a different state. The state is as a graph, object graph. The state, instead of having just full frame features squeezed out of the full frame, you have features squeezed out of each object, and their pairwise distances. And what can you do with the state? You can do whatever you like. I'll show you what you can do. The most trivial thing you can do is imitate somebody who is, demonstrating a task for you. Okay, so this is what you want to do. You want to find good states. So if somebody demonstrates something, for example, rotating that yellow pole, if the robot rotates the yellow pole correctly, you're going to have higher reward. And if the robot rotates the pole wrong, does something wrong, not like the human does, you should have low reward. Do you agree that this is very useful? This then the network will capture what is similar, what's not similar. And as you see here, the object-centric correctly says that, look, the wrong thing is indeed wrong. Very low reward once things go starting being different than the demonstration. While the full frame, because there are so many things happening in the frame, it cannot really focus on the important part. Does this make sense? So attention on the objects, let alone that we know from your science that infants can attend to objects extremely early, all right, as opposed to taking all the time the full image and, computing. So they constantly attend on objects, and putting such object attention into our architecture is going to help a bit. It's going to help a lot. And how can you train detectors without having labeled data? Well, the first thing you can do is background subtraction. So you get one single example, but then you can augment this data in a synthetic manner. You can just pasting masks around like crazy, behind the background of the object, trying to simulate all possible occlusions, etc., of the objects, and use these tons of synthetic training data. You see, many of them do not make any sense, but you generated them, and you can use them to train your object detectors. Does this make sense? Only from a single positive example. And in fact, this is shown to work really well right now for video segmentation. Just take something and hallucinate how it will look in different situations and use synthetic data generated in this way to train your detectors. And you do the same thing. And then you put, based on this X, the distance, okay? And then you show that very, very fast you can imitate a human demonstrating a task. Okay, after 3 iterations of your trajectory optimization method, we'll talk about this trajectory optimization method. While if you didn't have that attention in your architecture, you wouldn't be able to do it. So I had a lot of, not a lot, actually it's just 10 more slides, but maybe I'll show you next time. Something very important. There's going to be a station on Monte Carlo Research this Friday. It's going to be around 45 minutes. We'll see a lot of details, how it started, how it proceeded, and how it did fantastic last year, putting it in a training loop, which was a big innovation. So if you won't come in the station, the slides will also be hopefully available before the station, so that you can see if you need to come or this material, etc.